Okay, yeah, so as I said, so today I would like to give you a different perspective on SVD and show you another interesting optimization problem, because SVD can be also viewed from a different direction as essentially solving a variational problem, or variational or optimization problem that essentially means the same. So optimization problems generally mean that you have some function, can be arbitrary variables, and your task is to find the minimum of that function over some set. Then you can have constraints and so on. This is like a general optimization problem. Sometimes it's called variation, so optimization problem. Sometimes you can also hear variational. There is only a subtle distinction between the two. It's more like a nuance. That variational usually refers to the fact when this would not be discrete, but it would be like a continuous, like optimizing a function. I think I mentioned that before. But I will just use the words as synonymous. So this would be a minimization problem. There could also be maximization problem, but they are all optimization problems, and it's closely related to variational problems. And what I would like to do today is to tie the main result of this course, the SVD, to a very interesting optimization problem, closely related to the low rank approximation. And then as we will be at it, as we'll be doing optimization problems, I would like to show you another very important optimization problem, finding the best fit orthonormal matrix to a given matrix, or best fit rotation. So today it will be about solving some special, very important optimization problems which closely relate to linear algebra and will be useful for applications later. We'll need that in physics-based simulation and so on. Okay. And yeah, so the last class is on this December 9th, right? So this is like only 4 more classes. So I think the rest will probably spend just like reviewing and doing some practice problems for the finals, unless you guys have some other idea. What would you like to do? Does that sound reasonable? Yeah. There's always like lots of cool details to go and going through it again. Even when I was preparing the finals, like, what was this thing? Aha! So there's these aha moments which are probably worth going through again, to just like, so you remind yourselves what is positive, definite, and so on, and how to detect it, and so on. All right, so this will also be like a little exercise on optimization problems. So let's start with the first one. So I have 2. The first one is the one related to SVD. And the problem starts as follows. I assume I have as input an arbitrary rectangular matrix, n by n matrix. And the task is to find 2 vectors, x, which is of dimension m, and y, which is of dimension n, such that the norm of x is the same as the norm of y, and both are 1. And here is the main part, the Frobenius norm of A minus xy transposed is minimized. Okay, that wasn't very nice, but you got it. So this is the optimization problem I would like to solve now. And I want to solve it because this will essentially give you a different perspective on singular vectors. Because, a spoiler, the solution will be singular vectors in some form. But it's interesting that you can essentially derive it from first principles. Because this problem is interesting in its own right? So what does it mean? For a given matrix, for example, consider this matrix was a square matrix and was a matrix of an image, right? I was talking about the example of image compression. If you have a matrix that has like lots of elements, 256 by 256, you can represent them, for example, monochrome image in it, right? If it was color image, you could also do that. You would need different layout then. And then this you can view as sort of a poor man's image compression. Poor man's because all that you are allowed are only 2 vectors. Only in this case it would be only 2 256 dimensional vectors. Moreover, their norm must be 1, so there's an additional constraint there. And we want to approximate the image with this outer product of the two vectors so that we get as close as possible. Sort of similar to what I was talking about when we discussed SVD about the low rank approximations, right? But there I basically just said that there is this Eckart-Young theorem which tells that the truncated SVD is the optimal approximation, but it's very cool to essentially derive it in this simpler case. You can also look at it as a simpler case of the Eckart-Young theorem and derive it from first principles. So that's what I would like to do. So one thing we can realize immediately is that XYT, what is XYT as a matrix? This would be like a typical, like a simple final exam problem. Like what are the properties of XYT? So first of all, it's what dimension matrix? That's simple, right? M by n, of course, because otherwise I couldn't even talk about subtracting them, right? I can only add and subtract matrices of the same dimension. And what else is interesting about this matrix? We had this before, I'm just testing if you remembered that. It's an outer product matrix, right? So x was a column vector and y was also, but I transposed it, so now it's a row vector. So it's this funny outer product type of thing, right? So what can we say about the rank of this matrix? Nobody? And I probably didn't do such a great job explaining. So what could we say about the SVD of XYT? If I decompose it into some U, sigma, and VT, how do you think the sigma would look like? Yeah, we totally need to do some review sessions. I know it's been. So let's think about it. What is in this matrix? So, or how the matrix is built, right? So this is its outer product of these two vectors. They have some elements here and there, and it will create a matrix like this. This is for the case that n was more than m. And in every column of this matrix is just a scaled version of x, right? So what is the dimension of the column space then? 1, right? So that means that the rank of XYT is exactly 1, right? Because the same argument you could then say for the rows. It's also every row is the same up to a scale. So from the SVD you would see it immediately. Only the sigma 1 would be non-zero, and sigma 2 and so on to sigma whatever r would be zeros. That's how the SVD would look like. Okay? So XYT is a rank 1 matrix. So essentially this optimization problem is similar to the low rank approximation problem, except that we have these additional constraints, right? We don't want arbitrary rank 1 matrix, but we want a rank 1 matrix which is an outer product of unit vectors. If I wanted an arbitrary rank 1 matrix, I could say that I will just take this, where alpha is some additional parameter. That would only make the problem like a little bit more complicated, so we will just stick with this one. But this would be, this would be a general rank 1 approximation of that matrix, a low rank matrix approximation. Okay, so now I think I explained the problem we are trying to solve enough, or do you have any questions on that? Then the question is, how do we actually solve it, right? I don't think it's obvious at all. Actually, what would you suggest? if you are presented with a problem like this, we can make these final sessions a little more interactive, I would hope. I hope it doesn't discourage you from coming. So how would we approach this problem? It's really an optimization problem, right? So it's just written here what we need to do. We need to find the x and y, right? So a probably good first step would be to realize what exactly is this thing we are trying to minimize, right? So the first thing we can realize is that doesn't matter if we are minimizing this or the square of this, right? Because this has to be non-negative. So if I square it and minimize it, I must get the same result because for positive numbers, x squared is a monotonic function. So I can as well say that my objective, so this f here, when I talked about general optimization problem, that's my objective, or sometimes cost function, the function I want to be minimizing. So I can define the objective to be a function f hat. I will explain when we get a little bit further why I put there the hat. So this is just a technicality, essentially, that I just square it. Why do you think I'm squaring it here? It's because the Frobenius norm... Okay, actually, maybe I should have you remind this. What was the Frobenius norm of a matrix? I know I said it several times already, but it can't hurt to repeat. Those things you should actually remember. There's not a whole lot to remember in linear algebra, but the definitions you do need to remember.
So the square root of the sum of every element in the matrix square?
Yes, that's exactly right. That's a square root of the sum of the squared elements. That's absolutely correct, over I and j, where I and j indexes all the elements of the matrix. So I was not really recapitulating that again because I already said it many times. This is basically measuring the difference between the two matrices, right? It's essentially the Frobenius norm is the same thing as Euclidean norm generalized from vectors to matrices. So the reason I want to take the square here is that the square root goes away, right? Because if I take the Frobenius norm squared, then I have just this, right? So I don't have to worry about the square root, just to make the problem a little bit easier. And why do you think I put the 1/2 here? That's just just a convenience, because in a little bit I will be computing the derivatives of that, and this 2 will nicely cancel with the 1/2. Of course, the 1/2 doesn't matter there, right? If I'm minimizing a function, then doesn't matter if I minimize the function of half of the function or 100 times the function, right? Because what I care about is the result, is the point where the function attains its minimum, and that point, of course, doesn't change no matter how I scale the function. Okay, so let's take a look at that objective. So what I want to do first is to rewrite the objective in a different way, which will be easier to optimize. I guess I forgot all these arrows, huh? So already from here, we can see, I think we also discussed this before, that there is a different way to write or define the Frobenius norm. That's the trace of ATA. I think we had it right at some point. I believe when I discussed the trace, we discussed this. I think it's fairly. Is it clear to everybody, or shall I? Yeah, I think we had this. I mean, it's very easy. It's just a matter of looking at the matrix multiplication and figuring out what a trace is, and you see it's exactly the same thing. So I can write this using the trace, right? So let me rewrite this Frobenius norm squared, and this trace has the square built in. That's another reason for squaring it. So let's write it with the trace. So what do we get there? Oh, I forgot the trace. Okay, I'll do it again. Sorry. Trace A minus X Y transpose and A minus X Y. That sounds about right. Okay, you know what? Forgive me the arrows by X and Y. So that would be a lot of errors to write. So here I just applied this rule that the Frobenius norm squared is just a trace of ATA, where in this case the A is A minus XYT, right? Okay. Nothing special happened here. So now we can write it out, or let me take baby steps. So first thing, we just write out the transposition. So this will be A transpose minus YXT. Right, I just transpose this entire thing, and this is A minus XY. Does it look correct? Okay. Yeah. What's that? So here I Oh yeah. You are absolutely right. Thank you. Thank you very much. Yeah, I was missing a transpose there. And now I will just apply distributivity and I will write out the product. You might have seen that coming. So this is trace of ATA. Now let me really take baby steps here. So it's going to be plus YXTX YT. Let's not forget it this time around. And minus A transpose XYT and minus YXT A, right? Let's be careful. Yeah, I just wrote out the bracket, expanded the brackets, right? Now here comes some. Now we can just split it in all the traces, right? So here we'll get 1/2 of trace of ATA. Then this other term will be 1/2 of trace of Y X transpose X Y transpose. And here I have minus 1/2 of trace AT X Y T and minus 1/2 of trace Y X T A. Why could I do that in one word or one sentence argument? Because trace is a linear operator. So what is this? So the A matrix that was given to us, right? That's the input. So this thing is just some constant, right? It doesn't depend on X or Y, right? Now, how about this thing? This thing is interesting, right? What is XTX? Of course, matrix multiplication is associative, right? So as long as the matrix dimension match, I can put the brackets there as I please. So I can put them here, put them there like this, right? And if I do that, what is XTX? Remember, I have this assumption the norm of X is 1. Right? So that means that XTX is 1. So this is 1, right? So that means that this entire term is just 1/2 of trace of YYT. And do you remember the cool property of the trace? That in a trace you can actually, do you remember this? So let me write it like here. The trace AB is the same as trace of BA. If the matrix multiplication makes sense. Which here it does, right? Here I have the outer product, and I can just say that this is the same as if I do YTY. I just flip them, because that's from this trace multiplication rule. And YTY is like also 1, right? So this is also just a constant. This is just 1/2. This doesn't even depend on the matrix. So these first two terms, they don't matter in the optimization problem at all, which is sort of interesting. So what matters are the remaining two terms, right? So let's look at the first one. This was 1/2 of trace ATXYT. That's this term here. So using the property of the trace, I can write it as y transpose ATX, right? How about the other one? The other one, this guy here, that was y xta, and I can do the same thing. I can flip the y on the other side. So this is xta y. Do you see the next step? There is one more cool property of the trace, right? Which is exactly because yeah, they are transposes of each other. Actually, you don't even need any property of the trace, right? They are exactly transposes of each other. And what's the dimension of this matrix? So let's see. X was an m by 1, right? By 1. Y was n by 1, right? And A is m by n, right? So what is the dimension of the xtay matrix? Well, if x was m by 1, then x transpose is 1 by m, right? Then I go through m by n, and then I have y, which is n by 1. So this is not even a matrix, right? This is just a 1 by 1 scalar. This is a 1 by 1 matrix, right? So that means if I transpose this thing, I will not change anything, right? I don't even need any trace rule here. So this is just exactly the same thing. And there you start seeing the reason for the 1/2 or another. Maybe this was actually the reason, not the derivative, that it disappears here already. The term, these two terms are exactly the same. That's the point. And let me write it. So here it's. So if I put all this together, I can write this as some constant, something that does not depend on y or x, minus xta y, right? Because if it's just 1 by 1, then I don't even need the trace there, because trace of a 1 by 1 matrix is just the scalar itself, right? So that's reformulation of the objective, which is sort of interesting. Because that means that minimizing, let me write it down, minimizing this fxy over x and y such that the norm of x is 1 and norm of y is 1, I will not just do it again, just remember that, is equivalent to minimizing this minus xtay, right? Which is equivalent to maximizing xtay, right? And they are all subject, of course, to the same constraints on x and y, right? Because minimizing minus something is the same as maximizing. So let me define the function fxy. That's like a reformulation of our objective. I just discard some constants, whatever. Doesn't matter as long as the optimum is concerned. So let me define the function f to be x transpose a y. So now all we need to do is maximize this function subject to the same constraints. And this function, you will probably agree with me, is simpler than the original one. So that was the purpose of this reformulation. Okay, so everybody on the same page before I turn it to a new page. Actually, maybe before I do it, let's just realize what type of the function is, right? F is a function that goes from Rm times Rn and assigns a scalar, right? It consumes an x, which is an m-dimensional vector, y, which is an n-dimensional vector, and produces a scalar, right? So you could be looking at it as a height field over like m plus n dimensions, and what we are trying to do is to find the highest point of that function. But we must not forget about what makes it a little bit tricky are these constraints, right? So it's not just we had like one height field, more like the geometric picture sort of is we have this m plus n dimensional space, and there we have like a manifold, like a subset of that space. Actually, it's sort of easy to, if I just look at this one of them, let's just forget about y for a second and just think about this constraint on x. So the norm of x is 1. So what is it geometrically? X is an m-dimensional vector, right? So it lives in m-dimensional Euclidean space. But I cannot take any vector from that space. I must only take the vectors that have norm 1, right? And what set is this geometrically? The set of all m-dimensional vectors that have norm 1. Maybe it's such a simple question that you're like wondering why am I even asking that? It's what? Sorry, I didn't hear you. Set of all basis vectors. Maybe let's look at. Yeah.
Geometrically, it's like you have the equivalent of a sphere.
Yes. Hypersphere, exactly. Yeah. If we happen to be in R2, right? If M happened to be 2, which it could easily be, then it would be just a circle, right? Just a circle like this, right? In R3, it would be a sphere with radius 1, and in 4 dimensions, you have just the same sort of idea. It's sort of difficult to like imagine what it is, but the equation is still the same. So that's what's really going on here, right? We have this high dimensional space, and we are optimizing there over a surface of some manifold. We'll find the maximum of that. So this is a relatively standard task in calculus. I hope by now you have all seen enough calculus to know how to solve constraint optimization problems like this. So the method to solve this is using Lagrange multipliers. Have you guys all seen Lagrange multipliers? Yeah, okay. 2 years ago? It's not so bad, I've seen it more than 10 years ago. In this case, it's not so bad. The idea of Lagrange multipliers is very cool. So now we are facing this constraint optimization problem, right? If it was not constrained, would have been easier. We would just not have to worry. X and Y could be anything, but now X and Y cannot be anything. So somehow we have to take the constraint into account. But what Lagrange multipliers essentially let us do, there is more to it, but the first order approximate explanation is that they just convert the constraint optimization problem to an unconstrained one. They formulate the function called the Lagrangian, which introduces, in this case, 2, because we have 2 constraints, right? One constraint on x and one constraint on y. So here we need to introduce 2 Lagrange multipliers, lambda 1 and lambda 2, not to be confused with eigenvalues. So there's nothing, well, okay. It will have to do something with eigenvalues, as we will see later. But in general, those are Lagrange multipliers, just arbitrary 2 scalars. And I will construct a function called the Lagrangian, or L, which will have the original parameters of my problem, as well as the Lagrange multipliers as arguments. And then I will find the critical points of the Lagrangian will be the potential solutions of my optimization problem. So maybe it's easier to just do this for this particular example. So for this particular case, I have this objective function, and I need to express my constraints also using functions. So I can define a function g1, which is a function of x and y. Those are the real variables of the problem, and I will just say that g1 is 1/2 of x dx minus 1, right? So let's just realize what is g1. g1 is a function from rm times rn going to r, right? This is a scalar. G2 will be similar, except that it will be measuring the length of y minus 1. And why I'm writing it this way, I just want to put it into the standard formulation when I'm minimizing f, x, y. Let me put some arrows here to make it a little bit nicer. Subject to the constraints that g1 of x and y is 0 and g2 of x and y is 0. That's just very trivial reformulation of the problem, right? And what the Lagrange multipliers tell us is that the critical points of the original of this constraint optimization problem have to satisfy the following equation. Have to satisfy the formula: the gradient of f minus lambda 1 the gradient of g1 minus lambda 2 the gradient of g2 must be 0. So this is what Lagrange multipliers tell us. So let's see if we understand perfectly this equation. What does it mean? So here I'm looking at the gradient, right? That's where the calculus kicks in, right? If I did not have the constraints, the g1 and g2 there, what I would be doing to minimize or maximize, to extremize the function? Yeah.
So from the gradient to 0.
Yes, I would just set the gradient to 0, right? Because I have these constraints here, then I have to do this Lagrange multiplier business. But like if they were not there, just have the gradient be 0. So what is the gradient then? F was a function, let me write it here again, from Rm times Rn to R. So it's a function that goes from m plus n dimensions, right? And the gradient of the function is just one big column vector of the partial derivatives of that function. So I start by partial derivatives with respect to x1, and I would do x2, and so on, up to xm. And then I would put the y's, right? y1, and so on, up to, oh my goodness, I wasted all the paper, to yn. That's what a gradient is, right? Geometrically, it's the direction of the maximum increase of that function. I think we have been through that, right? What gradient is, or you know that from calculus, I hope. Is that clear? The same thing is also true for the gradient of g, right? The g is a function of the same type. So g1 and g2, of course, they both have the same type. So the gradient of g1 and gradient of g2 are the same thing. Those are just m plus n dimensional vectors. The same thing on the right. What is the 0 here on the right? That's also just an m plus n dimensional vector of all zeros. Okay, so this is essentially a way to conveniently write m plus n equations. Okay, because this is a column vector. This is also a column vector. This is also a column vector. This is also a column vector, right? Lambda 1 and lambda 2 are scalars. Make sense? So the question now is, what exactly are these gradients? We need to compute the gradients, which is slightly funny. Do you know how to compute gradients? What we need to do, so now we want to solve this problem. So we will have to figure out what exactly the gradients are, right? They have to be they are defined like this. That's just the vector of all the partial derivatives. So the first thing we could think about would be just to, okay, what was the definition of f? F was nothing but xt ay, right? And because here the coordinates of x appear, this is x1, x2, and so on, right? So maybe I could just make it like super clear by saying that x is x1, x2, and so on to xm. and y is y1, y2, and so up to yn. So I could just write this equation using coordinates, right? I could just make some sort of gigantic sum over xij, doing xi a ij, the ith and jth element, and here would be my y, j, and then I could start differentiating by x1 and by x2 and by x3. I don't know, how about you? I don't really want to do that because messing with all these coordinates is like a very, very tedious business. So a faster way to compute the gradients is by using differentials. It goes by different symbols, so I will just use the lowercase delta symbol. I will want to compute the differential of f. I'm not sure if you had this in calculus. We had it in calculus, but it was a little obfuscated there. Or sometimes it's called the total differential. Essentially, it is the locally optimal affine approximation of the function, or linear after I subtracted the value of the function at that point. So the best fit linear function. That's what the differential is. And the cool thing is that the differentials observe the same rules as derivatives. So if my f is xday, the differential of f can be computed quite easily. So this is just the differential of xday, which is in turn the differential of xt. So this is the product rule for differentials. xda, the differential of y. Now let's see to get it right. Now I can transpose this entire thing. So I can do yt at dx plus xt a dy, and then I can use some matrix algebra, so I can write this formula like this. So let me first write it down, and then we can discuss about it to make sure. So what happened in this last step was that I took this part here, transposed it, and put it in one row vector here. Because what is the dimensions of this? A times y. A was m by n, right? And n was a column vector. So this is an m by 1 row vector, right? Same thing would be true for the ATX, except it will be n by 1 row vector. So this is just an m plus 1 row vector, right? And guess what this vector is? That's exactly the gradient of f. Amazingly. Have you seen this before? This is like a very cool way how to do calculus on matrices. I guess the easiest way to understand this is intuitively. You can understand these delta x and delta y's. Like don't quote me on that. That's not like solid calculus. It's just more like the intuition. You can understand these delta x and delta y's as like some sort of tiny displacements. And this formula tells you if I displace the x's and y's, the two vectors, by a little bit, how changes the delta f, right? If I do a small perturbation to the x and small perturbation to the y, then f also changes a little bit. And the first order description of that little bit is exactly the gradient, right? So this is a very convenient way to compute the gradient, and all you need to know there is that the differentials observe the same rules as standard derivatives, and that this tells us that the gradient of f is exactly ay and atx. So it's an m plus n by 1 vector. Here, notice that here the gradient was transposed. By the way, if you really went the hard way and you took this coordinate expression, and then you really differentiate it by x1, then by x2, and then by x3, and so on, and then the same by y1 and y2, and so on. Ultimately, you could again fold it together and see that it's really equivalent to these expressions. So this is just like about elegance of deriving it. So how about the gradients of G1 and the gradient of G2? Could you guess it? So G1 was this function, right? That's our constraint function. The purpose of it is we set it to 0. But for as far as the gradient is concerned, it's just a function from x and y that assigns it a scalar. And if I want to compute the gradient of G1, what do you think that will be? So clearly it does not depend on y, G1, right? So there the gradient will certainly be 0, right? Again, that this is to be understood. It's a vector of n zeros. And if I differentiate the G1 by x, here this would not be so difficult to do by coordinates, right? Because this is such a simpler expression. I guess I can just do it if you want me to do it. Or do you want to take a guess? Well, let me just do it. So the differential of G1, so G1 is 1/2 of x dx minus 1, right? Right here. So the differential of G1 will be 1/2 of differential x dx minus 1, which is 1/2 of, now I apply the product rule, differential of xt times x plus xt times differential of x minus 1. There's no minus 1, the differential of a constant is 0, of course. Which, when I transpose this entire thing, then this is just 1/2 of xt differential x plus xt differential x, taking baby steps. So this is just xt differential x. This thing is the gradient transposed. The gradient is just x. Which is cool. Now the gradient of G2, what do you think is going to be the gradient of G2? Now you have a good, then you have a safe bet. Sorry, so, okay, you can say?
The same as G1 but with y.
The same as G1 but with y, exactly. So it starts with 0, and then comes the y, right? So now I understand this is m zeros and this is n coordinates of the vector y. By the way, all these, I don't really write it here, but all the gradients, of course, depend on at which point we are evaluating it, right? So this assumes I'm evaluating it at point x and y, which is an arbitrary point. Right? Okay, so now we have done the hard part, and now comes the fun part. That means actually solving this. Now we know all the gradients, so we can just plug them in there, right? So the gradient of f was ay and atx. That's for the gradient of f. So I'm just taking this equation and plugging in the gradients we have just computed. Minus lambda 1, the gradient of g1, which is x and 0. And here is minus lambda 2, the gradient of g2, which is 0 and y. And that has to be equal to zeros. And again, this is actually m plus n equations, but I like to write them together, so there's not that much writing. So I can split it into two matrix equations, right? The first one would read ay minus lambda 1x equals 0, and the second one would be A transpose X minus lambda 2y 0, right? Because the zeros, they don't really do anything there, right? We put there some arrows to make it clear that these guys are vectors. So this is the system of equations I need to solve. I still need to not forget about the conditions that the norm of x and y, it is still has to be 1. So one cool thing we can notice from this, so let's take a look at the first equation. What I can do, I can multiply it from the left with x transpose, which will give me this. X transpose x is 0, right? So I took the first, so those are the two equations. I took the first one and multiply with xt from the left. You can do that, right? And then why I'm doing that is because xtx is 1. That tells me that xtay is lambda 1, right? Now look at the second one. Here I can hit it from the left with yt, and I will get this. Yty is 0. So that means that ytatx is lambda 2, right? But remember, this is the same thing as before. Ytatx is just a 1-by-1 matrix, aka a scalar. So this is the same thing as xtay. That's the same thing as here, right? So from this we can conclude that the lambda 1 is actually has to be the same as lambda 2. So I can as well drop the subscript 1 and 2 and just call it lambda. Why not? And here comes the beautiful part where it will all click. So now I know I don't have to differentiate between lambda 1 and lambda 2 anymore. I can just write their lambda. So let me copy these two equations where I substitute lambda for both lambda 1 and lambda 2. So what this will give me is ay equals lambda x, and A transpose x equals lambda y. Right? So I just took these two equations, put this on the right hand side, and then realized that lambda 1 is the same as lambda 2, so I just call it lambda. This could already be looking familiar to you, but it will be even more familiar when I will let me just express the x from the first equation. So this means that if I express it from this equation, I will get that x is 1 over lambda ay, and then I can substitute this to the second equation, right? So I will get A transposed 1 over lambda A transposed ay equals lambda y. So what I did, I took this expression for x in terms of y, and I plugged it in here. So I get ATAY divided by lambda, right? And the right hand side is lambda y. Does everybody see this? Shall I repeat it again? So first I express the x from the first equation, and I see that x is 1 divided by lambda. I just divide the whole thing by lambda. That's it, right? So this is what the x is in terms of y. This is the relationship between the x and y, right? So now I have this expression for x, so I can plug it into the second equation, right? So here I get A transpose times, I just take this and copy it over there. Oops, yeah, I said that I did it wrong because I'm trying to hurry up. Lambda ay. And that's exactly this, right? The right hand side is lambda y. So this, or even nicer expression is this, lambda squared y. Now this should look familiar. It's an eigen what?
Eigen vector value.
So y, exactly. This is exactly the eigen vector, eigenvalue equation, right? This says that the y must be an eigenvector of ATA corresponding to eigenvalue lambda squared, right? On one hand, I really like to finish, and on the other hand, I should finish. Oh well, I guess I will just have to leave you with some of an overhang, and I promise you to finish on Wednesday. Okay, I will finish it on Wednesday then. It's almost there.